So let's begin. So my name is Siva Balakrishnan. I'm an assistant professor in statistics. And so today I'm going to be teaching, guest lecturing for Larry. And I'm going to teach a topic that's sort of more on the computational side of things. So you'll see a bunch of new definitions and so on. So just feel free to stop me if something doesn't make any sense. Right? And so the topic for today is boosting. So let me just sort of say what boosting is first. Jason, what is this? Should they pick it up now or after? After. Okay. Good. Okay. Okay. So at a high level, AdaBoost is sort of a very popular classification algorithm. And it's an algorithm that has had sort of very strong empirical success, but maybe it's even more interesting from a theoretical perspective, where it's a very elegant theoretical algorithm, and it has a lot of nice connections to things like online learning, loss minimization, many other things, game theory, and so on. And so exploring these connections has led to many fruitful interactions between both statistics and machine learning. So this is one of those algorithms that was developed by theoretical computer scientists, so people who are more in the machine learning half of the world. And it almost instantly piqued the interest of a lot of statisticians, particularly people like Leo Breiman. So Leo Breiman studied boosting a lot, and it resulted in him developing random forests, which are another extremely practical algorithm. And many other people, so Hastie, Tibshirani, and Friedman, who are famous statisticians at Stanford, also studied boosting and gave their own viewpoint on it. And so it's one of those algorithms that has a lot of controversy in terms of because there are so many different ways to think about it. But it's also something that's been very fruitful in terms of investigating boosting has led to a lot of new connections. All right, so let me begin with some historical context and tell you what motivated Rob Shapiro to come up with this algorithm. And to do this, I'll need to sort of explain to you what the pack model is. So I'm assuming you haven't seen this before, but if you have, hopefully it won't be too boring to see definitions again. But so the pack model is this probably approximately correct model. So by the way, how many of you have seen the pack model formally before? It's about half of you. Okay. So I'll define something which is the version of pack that was defined in Valiant's original paper. And so this is what people would call the realizable pack model. Right? And in this model, you have, so you say an algorithm A sort of pack learns some class of hypotheses H if so for any function h and little h, any sort of epsilon and delta which are positive, the algorithm has the guarantee that probability at least 1 minus delta, it'll produce some hypothesis G that satisfies this thing. So you draw samples from P, and then you look at whether G agrees with H or not. Right? And the probability that it doesn't agree with H should be less than epsilon. Right? And this is in the model where what you see is samples of the form x and h of x, which are drawn according to P. Okay? So the model just says you receive a bunch of samples, they're drawn according to some distribution, and what you're seeing is really x and some function or some hypothesis evaluated at x. So if you like to think about the statistical setting, this is like a noiseless problem. So you're seeing directly the function that you're interested in. And the goal of pack learning is you want to produce an algorithm that has this guarantee. So on a future sample, drawn from the same distribution, the probability that it will disagree with the true hypothesis H is less than epsilon. Right? And so there are two parameters here. This has to happen with probability at least 1 minus delta. So there are these two parameters, delta and epsilon. Right? So is the requirement clear? Feel free to stop and ask questions. Okay. So throughout the lecture, we're going to focus on a particular case. So this is a lecture about classification. So what that means for us is that h of x will be either -1 or +1. Okay. So now I have to explain what realizability means. So this is really the realizability version. So what it means to be realizable is that what you're seeing samples of is really h of x. So you're not seeing anything which is noisy. You're seeing directly samples. So there are two variants of this. One of them is where you actually see something with noise. So you see maybe there are two possibilities. So you can have random noise, which is you flip h of x with some probability, say eta. And the other is where you think of h of x as a regression function. Right? So the probability that y is 1 given x is this function h of x, and then h of x is, say, something that takes values in 0, 1. Right? So this is some other kind of what people would call noise. Right? So this is maybe what statisticians usually think of when they say classification. Right? So there's some unknown regression function that underlies the whole thing. And you can also assume that there's some function that has that form, but that function is not in your class. And all of these will fall under the setting of what, in the PAC world, this is what you would call agnostic learning. So we won't do any of those things today. And maybe importantly, one distinction is that PAC learning means you have to do this for any distribution P. So you're not allowed to make distributional assumptions. Yeah, so for it to be a true PAC learner, the guy who's using it will provide you epsilon and delta, and your algorithm has to satisfy that. Right? And okay, so yeah, I could obviously say set epsilon to 0, delta to 0, and then that would be kind of funny. So formally, interesting. How does one make this go up further? Okay, so let me write on that side of the board for now. So, okay, the other maybe requirement which will make everything make a little bit more sense is you want to do this drawing some number of samples n, and you want n to be polynomial in something like 1 over epsilon, 1 over delta, and maybe the dimension. Right, so this will be something. You can impose this as an additional requirement on PAC. Right? So then it will maybe make sense. Polynomial just means n should look like some function of these three things, which is a polynomial function. Right? So n can look, I don't know what, like d cubed over epsilon to the 4th times 1 over delta to the 5th. This is fine. So if you're used to normal dependencies, maybe n usually looks, I don't know what, d over epsilon squared log 1 over delta. Something like this is the standard dependence that you would get, but PAC is very loose in this sense. It will say you can do it with any polynomial. Okay, and maybe the other, so there's the agnostic versus realizable. And the other distinction that some people would make is what's called proper learning versus improper learning. So what it means to, this means that you have to output G which belongs to the class of hypothesis H. Right? So there's some hypothesis class that you're trying to learn, and your output of your algorithm must belong to that hypothesis class. And that's what it means to be proper learning. And boosting in general will be an improper learning algorithm. So it will output something which is a convex combination of base learners. And in general, that won't be a member of this hypothesis class. Questions? Okay, so think about the case where what you're trying to learn is what's called a linear threshold function. So that is h of x is the sine of some unknown beta transposed x. Right, so this is like a hyperplane, and the classification problem is sort of saying that if you're on one side, all of these points are positive. On the other side, everything is negative. Right, so what you're trying to do in this case is I don't know beta, and I want to produce a hyperplane so that the probability mass in here is less than epsilon. So this will be something that sort of resembles logistic regression, maybe without some noise. Other questions? Okay. So the second definition that we'll need is this idea of what's called weak learning. So we'll say that some algorithm A weak learns a hypothesis class H. So now you should again delta some positive number, and in this case, what it means to weak learn is that there must be some gamma. Let's say that it's strictly positive, such that with probability 1 minus delta, you output a hypothesis. So you output something G which is not equal to the true hypothesis H of x. And okay. And again, the samples that you're observing again are just x and H of x, where x is drawn from P.
Delta is a value that satisfies all distributions.
So think about it as it's some fixed small constant. You'll see why it doesn't matter, but yeah. So yeah, don't think about it as some distribution dependent thing. It's just some fixed small constant, and I want that with probability at least 1 minus delta, I should output a hypothesis. So now I no longer am requiring that this quantity is less than epsilon. I'm saying that it just has to be slightly better than random. So if I just randomly tossed coins, I would agree with H of x half the time. Right? And now I want to agree with it slightly more than half. Right? And this is what it means to be a weak learner. And again, this has to hold for every distribution P. So your algorithm, no matter what distribution I give it, it must return something which satisfies that guarantee. So is the definition of a weak learner clear?
I have a question.
I don't know who's somebody. Yeah, yes.
So is the gamma dependent on delta, or I think it should be changed all the time?
Okay, so think of delta small fixed number. And gamma is another small fixed number that's independent of delta. There's just some gamma that is small and fixed for which this is true. Okay, so we'll need some more notation, which is, okay, so let's say that you output some hypothesis G. It comes from some class B, which is a class of base learners. And just as a side note, we'll only require what are called empirical weak learners. So an empirical weak learner is you draw one sample, and then you keep reweighting this sample, and then you need this. So the distribution P is all some reweighting of a single sample. It's not super important what happened, but you don't really require.
You said gamma is small. Is there any significance to gamma being small? Just in practice, it's going to be
Well, so if gamma is large, then this is really similar to this, right? So there's no significance. I'm just saying it's a weak learner if there is some gamma that's positive. It's a strong learner if gamma is close to a half.
So is empirical weak learning equivalent to like definition?
So not exactly, but so empirical weak learning is, okay, just for the sake of convenience, I'm defining something, but really what it's saying is that you can evaluate the performance, right? So if it's just the performance on a weighted sample, I can actually test if you're a weak learner or not, which I can't do if it's not an empirical sample.
So basically, being able to be empirical weak learning something is a necessary condition for it to be for the entire thing to be weak learning.
Is every empirical weak learner a weak learner?
Unclear.
The other way around. Is every weak learner an empirical weak learner?
So neither of those are true.
Oh, okay.
So, I mean, an empirical weak learner says something about a particular sample. So it's somehow a statement conditional on a sample, right? So a weak learner is a statement about the population, which may or may not be representative of the sample. So neither of those two statements are true, really. But you can get away with a population weak learner through boosting. But you should think of empirical weak learning as an easier thing to check in practice, right? So if you back learn, then you've definitely weak learned. So the only distinction really is that here you're requiring it to work for an epsilon, and I specify a small epsilon. There you get to pick a gamma, and so you can say, okay, it works for some very, very small value of gamma, and that's a weak learner. So in some sense, the algorithm here picks gamma. And here the adversary or whatever picks epsilon. Okay, so
The realizable part is more passive than weak learning.
it's a harder requirement to satisfy. So if I say your algorithm has to be a realizable packed learner, that means I can say, here's a number, 0.0001. This is a value for epsilon. And you should be able to produce a hypothesis that's wrong on less than this fraction of the data. Whereas a weak learner, you get to pick a number. So you can pick a number that's, say, that small. And you have to be right more than, half plus this little bit of the data, right? So weak learning is sort of saying that you have to be right on just more than half of the data. And pack learning is saying that you have to be right on essentially the entire thing. Okay, so at a very high level, if you exclude whatever, n and d, which are these sample sizes and dimension, the two main parameters in the realizable pack model are epsilon and delta. So really in words, with probability 1 minus delta, you need to produce a hypothesis that is epsilon good. So this is what it means to pack learn something, right? And so there's sort of a fundamental question that was posed. So Leslie Valiant, who is the one who introduced the pack model, also made the observation that somehow this delta parameter doesn't really matter. Is essentially inconsequential. So what that means is if an algorithm A sort of pack learns for some value delta which is big but not 1, so strictly smaller than 1, then you can just run this algorithm many times on fresh samples, pick the best one, and that will be an algorithm that will learn for delta small. Okay, so let me repeat what this is. So what is the parameter delta trying to capture? It's trying to capture how non-representative your sample is. So in some sense, you're going to draw a sample from some distribution. Maybe you got unlucky and it looked nothing like the true underlying sample, right? And that's what has to go into this delta. But if you have an algorithm that learns with some weak guarantee on delta, you can just run it many times and then pick the best hypothesis. And you can do this using a fresh sample. Right? So somehow you can run an algorithm, so call this thing delta twiddle. If you run your algorithm roughly 1 over delta twiddle something, log 1 over delta times, then you can see that the best of those learners will in fact be a learner which has delta which is small. Right? Does this sort of make sense? You can. It's like a simple Markov's inequality argument that you can't fail to learn on too many samples. Right? So I can just keep giving you a fresh sample. Eventually, you'll have to produce a good hypothesis. So in some sense, this delta parameter is fairly inconsequential in the pack model.
How could we know which one is the best?
Say that again?
How could we know which hypothesis?
So you use another sample, right? So you can just cross-validate. And you can see that that will work. Okay, so the other parameter in pack is somehow much more interesting. And this is this epsilon parameter. And what you'll see is the distinction really between weak and strong learning is just that one of them works with a small value of epsilon and the other works with a large value of epsilon. So Kearns and Valiant at some point posed this open question as to whether, in some sense, weak learning is equivalent to strong learning or something. Right? Is it? So this is just whatever, realizable pack learning. So what that means is that if I give you an algorithm that weak learns, so you have some black box that says, okay, you feed it some data, it'll produce a hypothesis that's just better than random. Can you use such a black box to construct an algorithm that does extremely well? So it has error less than epsilon for some specified value of epsilon. And this was sort of a long-standing open question that Rob Shapiro at some point settled. And in fact, he showed that boosting is an algorithm that does achieve this. So in some sense, boosting is an algorithm that will take a black box to produce weak learners and boost it to give you something that is a strong learner. Questions? Okay. So let me first just describe boosting as an algorithm, and then we'll try to connect it to things you've seen before in this class, and then we'll prove a theorem about boosting. Okay, so I'm going to tell you what ADA boost is. So this is the most popular variant of boosting. So the algorithm is as follows. You're given a bunch of data. So each of these, so the x's come from some space x, and the y's come from minus 1, 1. So you're given n samples of this form. You initially weigh your sample. You set every sample to have equal weight. And then you run sort of t rounds of boosting. So t is now, you should think of it as some kind of tuning parameter. And in each round, what you do is you first call your weak learning box on the weighted version of the sample, right? So, oh crap. Okay, so let me move over here. So remember that I can pass to my weak learner any distribution, and it must still produce a hypothesis that is better than random. So in particular, I will give it the current weight distribution. So it's just the distribution I'm passing to it is a weighted version of my sample. And it will return to me a hypothesis h sub t. So this is the tth round of boosting. And let's define its error to be epsilon t. So this is the error on the distribution Wt. So this is the empirical error of the weak learner according to this weighted distribution. And then you choose a tuning parameter now, which is this alpha t, which is, and we'll see towards the end of the lecture why this comes up. And now you reweight your sample. All right. So first you did this, then you chose this, and now you update the weights on every sample. So in particular, you pick the weight at time t plus 1 on the point xi to be the weight at time t times Okay, so what are you doing exactly? So if you got the example correct, then this thing will be plus 1. So then you're down weighting. So every example that you get correct, the weight at t plus 1 will be proportional to the weight at t times e to the minus alpha t. And the weight at t plus 1 for the ones that you get wrong will go up. And then you repeat this argument. So then you pass this new distribution to your weak learner. It will give you a new hypothesis. You compute its error, and you reweight your samples. Right? So just intuitively, what is boosting trying to do? It's trying to reweight your sample in a way so that you learn something new from each round of boosting. So a weak learner gives you some weak amount of information. It does something slightly better than random guessing. But if I weight my points so that I'm putting a lot of weight on things I've gotten wrong so far, then I'm forcing it to tell me something new. Right? So even though it's a weak learner, it's somehow forced to give me some new information. And intuitively, that's all that boosting is doing. It's picking some magical parameters. We'll see why they come up. But then it's at every round, it's taking your weak learner. It's saying, did this weak learner get the example correct or wrong? If it got it correct, it's downweighing it. If it got it wrong, it's upweighting it. And then it's recursing this thing. And what's your classifier at the end of the day? So you're going to run some capital T rounds of boosting. And your final hypothesis, or your final classifier, is just the sign of So you're weighting each of your weak learners by their error rates. So if you had a good classifier, it'll get a higher weight here. And so you're taking some convex or some linear combination of your classifiers, and that will be your final boosted classifier.
So all the HT is trained use the original data, or use the reweighted rituals.
So at every step, you're reweighting, and then you pass the reweighted data to the weak learner. So it's giving you, it's trained on the reweighted data. Right? So HT is trained on WT. So it's weighted according to WT.
You use WT to regenerate a set of data.
You can think of it that way, but yeah, you can think of it as you take every point and weight it by this weight. But yeah, sure. You can also think of just sampling from that distribution a lot. But it's just some weighted data set. Maybe that's better. But the weights are giving you some distribution on the data, on the training samples. Yeah?
Is this guaranteed to converge in any sense?
Not always. So boosting can cycle and all those things. But here we're picking some finite t and running it for t rounds. There are examples empirically where it does not converge. There are guarantees of, like you can make a set of assumptions and then it will become like a coordinate descent algorithm, and then you can prove some convergence guarantees. But it doesn't always converge. Okay. So is the algorithm, the motivation for the algorithm, etc. clear?
What do you mean by weighting the data?
So you can think about it as, so what does it mean to, well, a weak learner, I give it as input a distribution. So I can give it any distribution. So one possible distribution is you take x1 comma y1 with weight. So this is now a discrete distribution with weight, whatever, WT of x1. Right. The second point will have weight WT of x2, and so on. Right. So this is now a distribution. These guys sum to 1.
So how about the continuous distribution?
So I'm playing the game, right? So I'm allowed to give it what I want. I'm giving it this particular discrete distribution. So think about it as you were originally given a sample that was something where each point had weight 1 over n. Now I'm just going to change the weights on every point, pass it back to this guy.
Then you sample
So the weak learner can do whatever it wants. It can, for instance, sample it. But I have to just specify a distribution from which the weak learner can draw samples. So in particular, once I specify these guys, the weak learner can draw examples from that distribution. So is the boosting algorithm clear to everybody? Okay. All right. So let's just spend some time trying to discuss various aspects about this, and then we'll finally prove something about it. Okay. So the first thing is, if you're used to a standard statistical setting, then the standard statistical setting is where you make some assumption about how the joint xy is, right? It comes from some joint distribution, pxy, and in particular, maybe there's some regression function, which is the probability that y is equal to 1 given x. And then you think about algorithms in this setup. Boosting is not designed generally to work in a setting like this, right? So in particular, boosting is designed to work in cases where you have essentially no noise on the y's. The fact that it works empirically in other situations is kind of strange, but a lot of the definitions, so things like weak learning and so on, will break in the agnostic case. And people have shown things like if you try to run boosting on a data set which has random noise, then it'll start focusing its efforts in trying to correctly classify points that it shouldn't be trying to, so in particular noisy points. So boosting as an algorithm is not designed to work in the agnostic setting, but there are a lot of people, so people like Avram Blum and Nina, who work on extensions of boosting to agnostic settings. And there, essentially, you have to modify the definition of a weak learner, and you have to modify a boosting algorithm for anything to make sense. So requiring an empirical weak learner is just too strong a requirement if you have noise. And so you have to weaken a bunch of requirements, and then maybe you can try to design new boosting algorithms. AdaBoost on its own is not supposed to be very noise tolerant. Okay, the second key point is, okay, so the main theorem that we're going to prove today is something about the training error. In particular, I'll show you that the training error after t rounds of boosting will drop exponentially fast. So it'll exponentially decay in t. And on its own, that's not a very meaningful statement unless you can somehow bound the generalization error of boosting. Does which bound?
In the second step, when you choose alpha, right, and it's such a specific form, is it because we need to use it for some proof? Or
Yeah. It'll come up from some proof. In particular, trying to explicitly minimize the training error as a function of alpha will give you this form. And you'll see it at the end. Okay, so proving on its own that the training error goes to 0, it may not be that interesting a statement because you usually worry about something like the generalization error. And so the generalization error is how well you would do on a fresh sample drawn from that distribution. And there are several ways to do this for boosting, and I'll just talk about one, which is the easiest case. So suppose that your class of base learners is finite, or say has finite any complexity measure that is finite. So finite metric entropy, finite VC dimension, any of these things. Right? And now I want to somehow bound the complexity of the boosted classifier. And the way that you do this is you make this observation that, say you're doing t rounds of boosting. Then first consider, so you've used some set h1 through ht, which are all in this class of base learners. Right, so let's say these things were somehow fixed first. Right, then the boosted classifier is just so the boosted classifier is just some linear combination. So in particular, I can think of if all of these are fixed, you can pretend that's a basis now. So this is just the sign of alpha transpose h. So this is now, I'm just replacing every data point by the value that these t classifiers give to it. Right? So you can see that this is, so once I fix t classifiers, this is just like a t-dimensional linear threshold function. And in particular, it'll have VC dimension t. Right, so the boosted classifier, if I fix the hypotheses, so I fix the base learners, then all you're learning somehow from the data is the alphas, and that has VC dimension t. Right, so since you have a bound on the VC dimension, you probably remember this. You can bound something like the shattering number given n points as, I don't know, in this case. Okay, and so this was some argument about fixed T-fixed classifiers. And so supposing that the base set was finite, then the number of ways you can pick T-fixed classifiers is just whatever, the size of the set to the T. And so you will get that the shattering thing, once you let the base classifiers vary as well, is just something that looks like that. Okay, so this is some complexity measure. It's a bound on the shattering number of the whatever boosted classifier when you're choosing weak learners from a finite hypothesis class. What is n? So E is 2.71 whatever. N is the sample size. So okay, what is this? This is the Sauer's lemma, right? So it's the something like that, right? So you sum this from something till t, and you will get some bound like that. So roughly, the shattering number for something with VC dimension t looks like n to the t. That's all that's saying.
Why do you want to calculate that?
Why do I want to calculate this? So because I want to give a generalization bound. So you should have seen these in your class before, but roughly the probability that the boosted classifier, I don't know what I call it, G. So the probability that G is not equal to Y is roughly always like the training error plus something like the log of that quantity. And so maybe you're used to seeing this with a square root, but whatever. It's something that looks like this, right? So if you can bound the shattering number, then you take the log of that, and that's something like the complexity measure. So the extra error you would get on an out-of-sample thing is bounded by something that looks like this. So have you guys seen this before? Okay, you have. All right. So okay, so just to say what exactly this bound looks like, it will look like T over n times something like log of n times b or something, right? So this is your excess risk or whatever, your generalization error. It'll go down as something like T over n. So provided you don't do too many rounds of boosting, your classifier is not that complex at the end of the day. So in particular, you can see that at the end of the day, we'll prove that this training error will look like e to the minus something like gamma squared t. So you would pick t to be some logarithmic quantity in 1 over n or something, log n. And you would balance out these terms. So after a fairly small number of rounds of boosting, you will balance your training and generalization error, and you'll get a bound that goes to 0 as you get samples there. Is this clear? Okay, so this is somehow only part of the story, and one of the reasons is that people have observed empirically that often boosting does not overfit. And this is sort of a very curious fact about boosting, that you can boost classifiers, your training error will keep going down exponentially, your training error at some point will hit 0, you can still keep adding boosting, adding sort of stumps or weak learners, and somehow your generalization error will continue to go down. Right? So there's some mysterious fact that happens on some data sets. It's not like a universal thing. But often boosting does not overfit. Yeah?
You're talking about the noiseless case, though.
Yes. Even in the noiseless case, your training error can go to 0, and your boosted thing will keep improving somehow out of sample. And this is a mysterious thing that it's not at all explained by this bound, because it's clear that once this hits 0, this is still growing in t. So you should really stop boosting if you believe that bound. Right? So you're creating a more and more complex classifier, but your training error is not improving after a certain point. And it turns out that there's a way to explain this via something called the margins theory of boosting, which is to say that people have shown that boosting actually will somehow improve the margin of your classifier. So the margin is something like y times h of x. Right? So even though you're getting all the training samples correct, it's producing a hypothesis that's somehow more confident as you do more rounds of boosting. And one nice thing about large margin classifiers is that you can produce a generalization bound that will be independent of t. So it's kind of a neat fact about boosting that there are other ways to prove generalization bounds here. So this is the most naive, which is to say every round of boosting increases the complexity of your classifier. But that's not the best way to do it often.
And so how is it that the classifier is actually it's adding new classifiers?
Yeah.
Right after it stops reweighting data.
Yeah. So you can keep boosting, right? Yeah. So it doesn't actually have to stop reweighting the data, by the way. So you're looking at the error of ht or whatever, the teeth guy. A weak learner will never be perfect. Right? So it will keep reweighting your data, and it will keep producing new classifiers for you. So
the reweighting is always done relative to the last weak learner, not the in-progress classifier.
correct.
Upper bound, like in the research field so far?
Say that again?
What is the tightest upper bound?
They're all sort of assumption based. So if you make an assumption that your data has a large margin, you can get a bound here that will depend on the margin. So say 1 over gamma squared, 1 over margin squared times n or something, right? So it will be a completely different style of bound. It won't depend on the number of rounds of boosting anymore.
We are talking about margin. Do you mean that the y is actually noise?
Say that again?
The y is actually noise when you are talking about margin?
No, I mean that, so you don't take the sign here, but you multiply y by h of x, which is something.
But h of x is like that case is like
So think of the case where I'm looking at what's inside before I take the sign, right? So it's just this part. This is not 1 or minus 1.
so y is actually the sign of inside of the sign.
So think about I'm defining margin to be something like sum over I, alpha I, hi of x times yi. And you can see that there are cases where you can keep increasing this quantity. If your original data has some large margin, then you can imagine that boosting can, even though it's getting the sign correct, it's going to make your regression function look more and more like 1 and minus 1. So it will somehow become more confident in what it's saying. But
Y instead of yi because it does not depend on the charge.
yeah, sorry. Okay, and so this is something about the generalization error, which is you can either use standard VC arguments to prove a generalization bound for boosting, or you can try to do more interesting things where you argue about the margins of your final classifier and say that it in fact achieves a better margin, and so you will get a nicer generalization bound sometimes. Okay, so the third thing that is here is that often you're interested in things that are called oracle inequalities. So this is, again, sometimes you're back in what's called the agnostic setting. You don't have a perfect classifier in your set of hypotheses. And what you want is a guarantee that at the end of the day, boosting will find you something that is as good as the best classifier in your collection of classifiers. And so this is in the agnostic setting, there is no perfect classifier. You want some guarantee that says up to some additive factor, you're doing as well as the best classifier in your hypothesis class. And one way to prove these is for boosting is via what's called the loss minimization perspective. So you can show that boosting has a close connection to what's called the exponential loss. And in fact, it will minimize the exponential loss via some kind of coordinate descent algorithm. And then you can apply things that you've seen to understand something like an empirical risk minimizer. So in particular, I don't know what, boosting minimizes exponential loss eventually. And again, this is going to be a fairly imprecise statement, but assuming this is true, you will minimize the empirical exponential loss, and then you can relate it to the population minimizer of the exponential loss. Right, so this is like an empirical risk minimization statement. It's just, at the end of the day, you can make the claim that boosting is really minimizing a certain loss function, and that's the exponential loss. And then you can argue about how the minimizer of that loss function behaves, and you will get oracle inequalities from arguments of that form. Does the statement make sense? So have you guys seen ERM before? It's like an analysis of something that minimizes some loss. Yes, no? Yes, okay. So you can analyze boosting in that same way. It does, in fact, minimize a certain loss function. Okay, so there's one last comment, which is how strong or weak is the weak learning assumption. So you've made somewhere an assumption, and that's the thing that's really doing all the work for you, which is that I will give you some reweighting of some data set, and your black box will produce for you something that's better than random guessing. And you can ask how strong an assumption is this, how rich does my base set of classifiers need to be for me to be able to satisfy this assumption, and so on. And this turns out to also be an active area of research, but you can make some relationship between whether your base set of classifiers can separate your data. So if there is some convex combination of your base set of classifiers that is correct on all the points, then you can show that your weak learning assumption will be satisfied in general. Right? So there's some connection to being able to perfectly classify using your base set to the weak learning assumption. Again, I don't want to say too much about it, but the weak learning assumption is in fact quite a strong assumption. And so there's a lot of work trying to say exactly how strong is this assumption. Okay. So finally, we're going to prove something. And this is going to be sort of the main result of the whole lecture, which is a result about the training error. So let me state the theorem, and then we'll prove it. Okay, so suppose I define gamma t to be 1/2 minus epsilon t. So epsilon t is the error rate of your tth weak learner. So gamma t is something that I know is strictly positive. And now suppose you start from any distribution W1. So you should think of this as 1 over n on all the points. But you could have started from any distribution. Then the training error. So what's the training error? It's the error if I sampled from W1 of my boosted classifier. Is at most something which is the product of the square root of 1 minus 4 gamma t squared. Okay, and in particular, it's less than okay, so what is this statement saying? You start from some initial distribution that equally weights every point in your data set. You run t rounds of boosting, and your error is going to look like e to the minus. You should think of every gamma as being lower bounded by some small constant. So it's something like e to the minus t gamma squared. Questions about the theorem? And somewhat importantly, this theorem does not rely on any probabilistic assumptions about the x and y. So you could have placed your points in an adversarial manner and or in a completely deterministic fashion, and you will still get a result of this form. And the key point is somehow the weak learning assumption is doing a lot of work for you. Okay, so let's prove it. And so in particular, we'll prove it by sort of unraveling the weight of every point. So the first thing to say is, what is the weight at iteration t plus 1 of the ith point? And it's easy to see that this is the weight that you started with, which you should think of as 1 over n. And then, so there's all these normalizing constants for the weights. But at each round, what happens to the weight is just becomes e to the minus alpha 1 So at the end of round 1, you're just going to multiply the weight by this amount and then renormalize it that way. Right. And similarly, for round 2, you would look at whether the second classifier got it right or not and reweight it like that. Right. So this is just the final weight of every point, is some product of the weights it gets at each iteration. And the nice thing is that this is very simple. So there's something in the denominator, which is this normalizing constant. So there's these t normalizing constants, but what's in the numerator is very simple. Right? So in particular, sorry. So this is just your boosted classifiers before the sign. Right? Let me just ignore the sign for now, but so before we go further, let's just try to think about what's going to happen in the proof. Right, so we're going to show that this quantity here, the product of the normalizers, is exactly this thing. So it's some exponentially small quantity. And at the end of the day, if your boosting classifier got the particular point I wrong, then this will be a positive. So this will be negative. So this will be e to the some positive thing, right? So for every data point that you classify incorrectly, you will get an exponentially large final weight. But remember, each of these weight distributions has to sum to 1. So in particular, you cannot misclassify too many things. Right? So at the end of the day, if you have to misclassify a particular sample, it really means that a lot of your weak learners have to have misclassified it. And if that's true, then you kept increasing its weight through many of the rounds. So it really has an exponentially large weight at the end of the day. And so you can't have that happen, and hence you can't have misclassified too many things. And that's what's going on in the proof. So what we need to show somehow is just first that the product of the normalizers is exponentially small, and then we need to use this fact about the weights that they sum to 1 to bound the training error. Is everybody clear on what we're trying to do? Questions?
Maybe it's better to use another board so we can refer to the theorem.
Sure. I'll push it up in a second. But I mean, I want to leave that part. I don't know how one uses these. Oh, I see. Oh, that one's stuck. I see. Okay. So they're both stuck. No, oh, fuck. All right. So, okay, so we're going to lose this part of it. Okay. Oh, okay. Okay, so the next step is going to be to try to prove that the normalizing constants are all less than 1, and in particular, the product looks like that. All right. Okay, so what is the normalizing constant at round t? So this is just the all those m's should be n's. Okay, so the normalizing constant is just the sum of the weights. So it normalizes it to be a distribution. So I can break this up into two sets of points. So there's the points on which your weak learner at this round got it correct. And these all get downweighted by alpha t plus the ones that you got wrong. Of the weight times e to the plus alpha t. And you should be able to check that this will just be 1 minus epsilon t. So there's some fraction of points that you got wrong, and there's some fraction of points that you got right, and those are these epsilon t's. So you get some epsilon t fraction correct, And so we'll look at, so epsilon t fraction of them get weighted up by e to the alpha. The 1 minus epsilon t fraction get down weighted, so they get weighted e to the minus alpha. And the point is just that the way that alpha t is chosen, so alpha t was chosen to be some mysterious number log 1 minus epsilon t over epsilon t, and it's actually chosen to minimize this number, right? And in particular, once you pick it, you will see that, well, this is exactly equal to square root 1 minus 4 gamma t squared, where gamma t is half minus epsilon t. Okay, so essentially what you're doing in boosting is you're picking these alphas to make the normalizing constant as small as possible, right? And at the end of it, you will see that you will pick a normalizing constant that will be slightly smaller than 1 at every round. Okay, so now we just need to finish the proof. We need to show that the training error roughly looks like the product of the zt's, right? And then we're done. So in particular, this is the training error. We need to show that it's upper bounded by this thing, which is the product over t of zt. And this last step is what will reveal some connection between the exponential loss and what ADA boost is doing. Right? So the training error will be upper bounded by something which looks like the exponential loss. So I'm going to now erase the theorem. Okay. So just to remind you, what is left to prove is just that the product of the zt's is an upper bound on the training error. So the training error is just you sample x from W1 and you check if your boosted classifier was not equal to y or not. This is the training error, which is the so it's the weight on the point times an indicator of whether yi times. So your final classifier, if it got it wrong, then this thing will be less than 0. Right? So every misclassified point, the sign of g will disagree with y. So y times the sign of g will be negative. Okay? And this is the step. Okay, so this you should think of as the 0, 1 loss of your classifier. And you would have seen these pictures before where you're in classification. One thing that you're often doing is minimizing some kind of surrogate loss. So something that's an upper bound on the 0, 1 loss. In particular, boosting is minimizing something that's related to what's called the exponential loss, which is the exponential function. And so this is saying the exponential loss is an upper bound on the 0, 1 loss. And now we just need something from here which says, okay, so I have this thing which is W1 times e to the minus yi gi, which is really equal to Wt plus 1 times the product of the normalizers. So this is equal to the sum over I equals 1 through m. N. And then I'm done, right? So the sum of the weights is 1, and so this is just the product of z sub t. So essentially you can see how we're putting the pieces together. That thing is telling you how the final weight behaves. This part is relating the final weight to the error of the classifier, and then the normalizers is what relates them, and that we've bounded somewhere up there. So if you put all of this together, you get this theorem that says that after t rounds of boosting, the training error will be some exponential of minus t. So I think we're essentially done, unless people have questions. And okay, maybe one point to observe about this whole theorem is that it never really used any probabilistic assumptions on the data. Right? So you could have taken any set of data. All the work is being done by the weak learning assumption. Yeah?
So one thing is that we mentioned, right, was this weird feature of boosting that it doesn't seem to be overfitting as much as it should. But in some cases, right, if you run classified cross validation error keeps going up, is there like a intuitive characterization of when that is the case?
Yeah, so basically, if your data has what's called an L1 margin, then it is true that boosting will not overfit. Or, okay, that's not exactly correct, but you can prove a generalization bound for boosting in terms of the L1 margin of your data. And so it will be independent of t. So, yeah. So there is a paper by Peter Bartlett, Yoav Freund, Rob Shapire, and maybe somebody else. It's called Boosting the Margins or something like that. And that paper does relate the margin to the generalization error. Other questions?
So what is typically a weak learner?
So people usually think of something that has high bias and low variance, so things like stumps. So, okay, one, you think about a decision tree, right? So a decision tree says you split on a variable, go down, you keep splitting on different variables until you get relatively pure nodes at the leaves. A decision stump is something that just says take one or two splits. It doesn't care about the final error, it just makes a few splits to improve the error. Right, so that's something that people often use as weak learners. Does that make sense? So let me draw you a picture of what. So a decision tree. So your data is in some box. So there, in this case, there's 2 dimensions, x1 and x2. A decision tree says, okay, so there's some data. I don't know. So it'll say, okay, if you split here, your classification error will go down. Right? So that, and a decision tree tries to keep splitting until it gets pure nodes at the leaves. Right? So that is, it says, is x1 bigger than half? And then it looks at, is x2 bigger than half? If so, label minus. If not, plus. I don't know. Do you see what I'm saying? Okay, a decision stump would be take only one of these or take only a few of these. A decision tree is something that you grow to a large depth. A decision stump is something that you grow to a small depth. And those will usually be weak learners. Those are what people use empirically as weak learners.
Are there any region to prepare distance term rather than full tree, except computational?
Well, so it's a good question about, so this is what random forests and other things do. So decision trees on their own are known to overfit significantly. So you have to grow a tree and then prune it back somehow to get a good classifier. A different way to do it is to pick something that has high bias and low variance. So this, which is something like a stump, and then boost things like that. And then it'll turn out that you won't overfit as badly. A different thing you could do is what's called bagging, which is you draw subsamples of your data, grow a tree on all of those subsamples, and average those trees. Right? And this will lead you to something roughly like a random forest. So decision trees on their own overfit, and there are various ways to fix this. One of them is to use short trees and then boost it. The other is to use full trees and then average many of them.
So what if I
I mean, no. As in, I guess you might reduce the variance again if you do it, but it's not completely obvious what you will gain. So people don't usually boost fully grown decision trees, for example. So a fully grown decision tree would be something like a strong classifier. But the reason why you don't want to do that is because your generalization bound depends on the complexity of your weak learners. Right? So if you're going to boost something that is already complex, you will pay a penalty in your generalization error. So usually people would avoid doing that.
First wrote down the 3 steps, right? Choosing alpha and then eventually choosing the, having the, I think it was behind this. First wrote down this, I had some thoughts, and I don't know whether it's related. How does it relate to run in motion? Or anything, because the last statement is very similar to, because each step depends on the previous step and there's some relevant elements to it.
So even though that sounds like a random question, there is some connection to sort of Brown boost. There's an algorithm that sort of makes this connection to the learning rate of boosting and sort of doing some. There's an algorithm called Brown boost that actually does make this connection. I don't know what it is. There is some connection. Yeah, it's Joachim Freund's paper. But all right, guess you guys are free.